Okay, well, this presentation is about some of the stuff that I do when there are cloudy nights and not so cloudy nights. I like to build things. And as you can see, I've attached a finder scope to a drill so that, it helps you drill, straight holes. So really this is about how to focus telescopes and the things that you use. And why do we actually need focusers? Because you're not changing the lens, and the mirror is always the same size with the same focal ratio and focus points. The point is that all the eyepieces are different. And the main lens or the main mirror will always focus the image at a specific point, according to its focal length. But yet the eyepieces have 5 millimeter focal point, 25 millimeter focal point, 40 millimeter focal point. So you need to move the eyepieces, the various eyepieces, back and forth until those two focal points coincide so everything is sharp. So that's why we need focusers. This is a picture I took at the eclipse down in Kentucky. There are many different kinds of focusers. I'm going to talk about this one. It's called a Crayford focuser. And if you can't buy a Crayford focuser, you can always, just print your own. Well, what do I mean by that? It sounds a little crazy. What do I mean by Crayford? What do I mean by print one? This is a basic Crayford focuser. And it consists of a tube that you put the eyepiece in. There's a ball bearing which rotates, which rolls here, and there's another one on the other side. There's another ball bearing here, and another one you can't see on the other side. And this tube will slide along those two ball bearings. This axle presses against the tube. So when you rotate that knob, it puts pressure, friction pressure, on this tube, and the tube will slide back and forth according to how this axle is rotated. Here's a spring. It just keeps the pressure on the tube. This is a 3D printer. Now, what does a 3D printer do? It takes a piece of spaghetti plastic, this white plastic, on this spool. It runs it through a heater. That's why there's fans on it. And that plastic is extruded out, that little tiny nozzle right there. We have a motor here which moves this extruder in the x-axis. We have a motor around the back that you can't see which moves this table in the y-axis. And there are two motors here which raise and lower this whole contraption in the z-axis. I'll get into that a little more in a second. Here are typical Crayford focusers. These I just got off, the internet, and they all have the same basic configuration. What you have, again, is the tube that the eyepiece goes in. There's that little axle right there. You can just see it with the focusers. And you rotate this knob. That axle rotates, and the whole unit rolls up and down against the ball bearings, which are inside that you can't see. These are a little different because they have a coarse adjustment and a fine adjustment. This coarse adjustment racks it in and out, and the fine adjustment is usually a 1 to 10 gear reduction, so you get very, very small adjustments. So what do? I use a program called Machine Shop, and there's a lot of programs out there. You don't have to use this. There's SketchUp. There's all kinds of different free stuff on the internet that you can use, and you can design the part. It takes a little learning curve. You got to be able to do it. And I want you to look at, where are we here? Okay, I want you to look at this part here, this horseshoe part, and I'm going to go back one slide. Whoops, wrong way. Hang on. Never mind. Previous. Remember this piece right here? This piece right here. That is this plate here. That plate right there. that plate right there. And of course you can't see it here because it's underneath. Okay, I got to get used to this one now. Okay, now remember I said that that z-axis raises up and down. That's because when you make your model, you have to slice it into about, well, it depends how big it is. This one is, I guess, about 100 slices, so that the plastic is laid down in one layer with the X and the Y, and then the Z-axis moves it up one notch, and more plastic is laid down, and the Z-axis moves it up again one notch, and each of those notches is a slice in the model. So you have to slice your model, and I use a program here called Cura, and you don't have to use this one. There's a whole bunch of other ones out there. It doesn't really matter. And if you look here, layer count, 96. Estimated time to print it, 1 hour. This is a program called Repetier, and it is the one that I use to actually control that machine. It talks to the machine, it tells it what to do, and it will lay down all those different layers in the model. When it's finally made, it'll look something like this. Now, these bars that you see here, those crack out. Those are not part of the model. When the z-axis gets up to this layer here and starts extruding this layer, there's nothing below it to support the plastic, so that'll sag. The program puts in these little support bars so that the plastic has something to rest against as it cools. And when it's finished, you just take a screwdriver and you just crack those things out. And there's the model that fits against the back. And this is a little movie, I hope it works. There we go. That shows the heated extruder here laying down the melted plastic as it builds up the model. And when it finishes that layer, the Z motors will drive it up 1 fraction of a millimeter, and it'll start again. So this is basically what it looks like when the printer's working. It's extruding plastic out onto that bottom bed. All right. Okay, so there's that piece. Those little supports have all been cracked out of there, and now we're tapping holes. This is where roller bearings are going to go. Those little roller bearings that help guide the tube that holds the eyepiece. There's bearings go in here and bearings go in here, and I'm tapping threads so that the bolt will hold the bearing in place. And these are the roller bearings that fit in the slot. These are what roller bearings look like in my hand, and this is what they look like in a diagram. There's little ball bearings in a race, so that the outer part will rotate almost frictionless with respect to the inner part. Now this might be a little hard to wrap your head around, but we need to put pressure against that spring that I showed you way back. You need pressure against the tube. This bolt screws into here. It floats in this member here. So the bolt really has nothing to do with this block. When it's screwed in all the way, the end of this spring, which is compressed, will press against the shoulder in here and push that whole block forward so that the axle is pushed against the tube. It's kind of hard to figure when you can't see what's going on inside, but that's basically what happens. Here's my completed focuser, and I've added a couple of extra things. I've added a tension adjustment so that if you put a heavy eyepiece in, it doesn't pull the tube, and I've put a eyepiece lock in there with a little nylon bolt so that your eyepiece doesn't fall out. And you can watch that work. Works very nicely. You can see how that moves the tube in and out, nice and smooth, right? Okay. Now, the next project is a different type of focuser. It is a helical focuser. Now, I took this picture a year and a bit ago, I guess, less than a year ago. But since there's some really good astrophotographers in the group, I'm kind of embarrassed to show some of these things. But anyway, this is a helical focuser, and it can be as simple as plumbing parts that you buy at Canadian Tire. When this part goes in the telescope, this part holds the eyepiece, and when you rotate this, it has the threads on it, screw it in, screw it out. It has a limited range of motion, but costs you $1.50 to make. Not too bad. I built something a little different, and this, again, has these roller bearings on it. I'm going to go back to the plumbing part one for a second. These threads are on an angle. That's why it'll move up and down when you rotate it. That roller bearing is on an angle, so that when you rotate the tube, it'll thread itself up and down within the focuser. So this is what the part looks like when it's designed. Here you can see the 5-degree angle with respect to the horizontal. And this is my completed focuser. And hey, lucky break. 1 1/4 inch plumbing piece from Canadian Tire, fits an eyepiece very, very nicely. So let's see a little closer up image. There's my roller bearing, there's the bolt holding it in, it's pressing against the tube. And once again, we can watch how that works. You can see how it smoothly screws in and out, right? Just like that. All right. So that is the first part of my presentation. I have another second part to go, but I stop for a second. If you want to shout out any questions, I'll repeat them so the online audience can hear them. If anybody wants to jump in for a second and just ask something, I'll be happy to answer that before I proceed. Just keep going. Yeah, please. Who's asking? Okay, go ahead.
What kind of plastic are you using?
What kind of plastic?
Yes.
The plastic that I'm using is called PLA. It's called polylactic acid. Lactic acid is the same chemical that makes your muscles hurt when you exercise too hard. And so it is biodegradable. It is organic. And it won't last 1 million years at the bottom of the ocean. So it's very biocompatible, if you want to call it that. Okay, please.
In your first Crayford focuser,
yeah.
What was the advantage of actually making the eyepiece tube, building the eyepiece tube, as opposed to using a tube like you did in your helical focuser?
I don't know. I just wanted to do everything. You know, I mean, once you're building something, you keep going. You know. I'll be taking the easy way out in a minute here. You'll see that. Please turn on the mic. There you go.
Okay.
Good,
Thanks.
good.
Yeah, one comment and one question.
Sure.
The question is, can you share the STL files?
Yeah.
Okay.
Absolutely. Give me your email, and I'll email
talk
it to you
afterwards about
yeah,
it.
Yeah, that's fine.
And the other one is, I live in Newmarket, and the library there has 2 3D printers
Right.
that you can basically get time on, and
Yeah,
I
yeah.
believe that other
Yep.
libraries do the same.
Yep.
So it's a nice, convenient way
Yeah.
to do it. They only charge you for the material.
Sure.
I think it's like $1.60 a meter or something. So
Okay.
it's pretty cheap. You probably got about $5 worth there or something.
Oh, that was about 4 meters.
Yeah, so 6.5 bucks.
Yeah. The problem with the library, they have a time limit. It may be only an hour. Yeah. Some of these things can take 2 or 3 hours to print.
Yeah, I mean, I've printed for 4 or 5 hours.
Exactly.
And on Friday, they have an all-day long print session, so
Cool.
you can do
All right, you got it then. All right, good. Any other questions right now? Okay, I'll keep going. All right, good. So I took this photo about 3 years ago in August. And if you're familiar at all with the sky, this is Sagittarius right here. and a couple of Messier objects right here. And let's, I've got a slide that shows them just a little clearer for you to see. There's Sagittarius, the teapot of Sagittarius, and there's the two nebula. And you can see the Milky Way comes out of the spout of the teapot like steam rising out of a kettle. It's kind of nice to see. You can see it as a time exposure because there was a boat going across the water here. Anyway, I like building things, as I was saying, because it's really interesting for me. And if you need something, obviously you can borrow it, buy it, you can build it. I like building things, and I think building's fun. It can be frustrating, at times. Things can, blow up in your face, but for the most part, it's an enjoyable exercise. Anyway, why in the world would you want to build something when there are so many high quality pieces of equipment that you can go out there and buy? And there's some amazing pieces that you can go out and buy. Why would you want to build it? Well, for all these reasons. It's fun, it's creative, lots of cloudy nights, especially this winter. It feels good when you build it, when you actually build something that works. My main problem is I like it to solve an issue. I'm observing, there's something that's really annoying me, and I figure, you know what, if I can solve this problem, it's going to make observing a lot easier and a lot more enjoyable. So what kind of problem am I talking about here? Well, have you ever tried to focus on a moving object? You touch the telescope, it jiggles. You touch it again and it jiggles again. And you turn the focus and maybe it doesn't look quite right and you want to go back a bit and it's still jiggling, and it drives you nuts because you can't focus the telescope on a jiggling moving object. So what did I want to do? I wanted to build a motor so I could hands-free focus the telescope without touching it. And that way, at least I had an advantage. This is a typical microfocuser. If Blake were here, he would recognize that he got this for me from the estate of Jeff Garrity. And this part here screws into the telescope. This part here, the eyepiece. And just like I showed you on some of those other ones, there's a 10-to-1 gear reduction on here. Why do I call it Hocus Pocus? What's so Hocus Pocus about it? Well, it actually is pretty involved. You need to know a little bit about electronics, expensive parts. You need to understand how to use those computer programs that I showed you on the previous presentation. CAD means computer-aided design. CAM means computer-aided manufacture. I'll call them advanced tools and equipment. You have to be able to build circuit boards and then troubleshoot them when they don't work the first time. This is what you're going to need to build this thing. A stepper motor. I'll get to that in a minute. You need a driving circuit for the stepper motor. You need a gearbox assembly for the stepper motor. Then you have to have a telescope interface. Then on and on and on and on and on. There's all these little parameters that need to be worked out, and lots of tools, electronics tools, drill presses, milling machines, like all this kind of stuff. So what's a stepper motor? Well, a stepper motor essentially is a motor that has 4 coils in it, and when you apply a pulse of electricity to each coil in succession, the motor will turn in discrete steps. The nice thing about that is you know exactly how far that motor turns per step. So you can have a computer count the steps, or you can have a computer tell that motor how many steps to turn, and it knows exactly how far it's gone. Why is that important? Well, your hard drive has a stepper motor in it. How does the computer know where to read that spinning disc down there inside there? It remembers I have to tell the stepper motor to move here, to move the read-write head a certain place to pick up the data on the disk. Your go-to telescope has stepper motors. You program into the hand control, which is essentially a computer, what you'd like to watch or look at or observe. Telescope knows where it's pointed to start with and will turn in discrete step motion to the place you want it to be. So stepper motors have a lot of uses in all the daily life. They're used a lot in cars to open and close vents, things like that. They're all over the place. Okay, so let's watch one work. Here's that driving circuit I talked about. So you can see that the motor's working here. It's rotating. I'm applying pulses to each coil in turn. And what I can do is I can adjust the rate of the pulses. And that will speed up or slow down the stepper motor. So here we're really giving it a lot of pulses. And now, look, you can almost see the individual ticks. See each little tick? That's each coil being energized in turn. And then you can speed it up. And if you want to, what you can do is you can then send pulses in the opposite order, and it will go the other way. So that's what a stepper motor does. Very, very important, very useful. Okay, what is a microcontroller? Well, we got to somehow control the stepper motor. So a microcontroller has a little bit of program space in it, a little bit of memory space, small, inexpensive, easy to program. All that stuff has input pins, output pins, all these things that you define when you program it. Very simple. An input pin, what would you use that for? Well, if you press a switch, the input pin will sense that a voltage has changed. Well, the program you put in there says, you know what? When a voltage changes on that pin, I better do something like send out a pulse to the motor. That's the difference between an output and an input pin. That is a microcontroller. Fits in your hand. This is my original motor controller box. Look at this thing. It's enormous. It has a timing clock module on it, and you change the pulses per second with this little control adjustment over here. It has 1, 2, 3, 4, 5, 6, 7, 8 output transistors in it. It's got logic chips in it. It's a zoo, and it took a lot of time to build, and it was a big deal at the time. This is what the circuit diagram looks like. Crazy. You don't have to understand what it does, but then again, there's the 1, 2, 3, 4, 5, 6, 7, 8 output transistors. And this is the circuit board that I had to build. I had to design it and mill out the circuit board, and it worked great. But it's big, it's heavy, and it uses a lot of power. Let's watch the pulses changing. Here's the driving circuit. This shows you on an oscilloscope how the pulses to the motor will change when you adjust down at the bottom. So let's stop. Oops. Oh, come on. Previous slide. Let's do that maybe over here somewhere. Okay. I don't know if you can read it. This says 2 volts. That means 2 volts for every little box here, every little division. So here you can see we got 5 volts, drops to 0. Time goes by. 5 volts, drops to 0. Time goes by. Those are the clock pulses to tell the motor each step how to turn. All that stuff in that great big box that I showed you, welcome to 2019, okay? This all fits in your hand. This little chip right here, that's got those 8 big driving transistors in it. This thing, this has all the logic in it that says how fast and in what direction to run the motor. There's actually 8 little lights on here which shows you when the pulses are being sent out. So, I just went out and bought that. $3 for both those things. It's unbelievable. It took 4 or 5 weeks to get from China, but for $3 or $4 you can do that. And less time, less cost, less size, less power, less debugging and troubleshooting. This is the program that you use to put the information into that microcontroller. And as I told you, you decide. Button 1 is this. Motor pin 1 is this. We're going to say button 1 is an input. Button 2 is an input. Motor thing is an output. So I'm not going to bore you with the details, but you lay out the whole pattern of pulses to the motor in this program, and then you load it into that microcontroller through a little cable. Well, proof of concept. Let's watch that work. Okay, so there's those little lights there showing each pulse going to the motor coil, and you can see that it is turning. And if I changed it so that the pulses would go in the opposite direction, the motor would turn in the opposite direction. So that's basically what we got going on there. Now, here's that focuser, here's that motor, and, well, just as an aside, a number of years ago, we used to have meetings at the DDO on Saturday nights, and people would present stuff and be interesting little topics and things. And I gave a couple of presentations about things I had built, which a lot of people were horrified because I used to drill into various pieces of telescope equipment. One fellow walked up to me after one of the meetings and said, "How could you drill into that telescope?" And I said, well, for that one, I think it was a 3/16 inch bit, as I remember. But anyway, the point is that this is far too nice a piece of equipment to drill into. It's not in me. I can't do it. And I needed to design something that actually fit on it and clamped on it, instead of drilling and holding it in. So that's where this piece of lucite comes in. You can see it's split here with a hole, and this piece of lucite will fit on this shoulder right here. This is the drive gear attached to the motor. This is a drive timing belt, and it will wrap around the coarse focusing knob. So let's see where that goes. There it is. So it clamps on, tightens up with those wing nuts. Lucky for me, those little teeth on the drive belt really nicely fit the teeth on the coarse gear. So let's see how that works. Here's the split adapter, and you can see how it, opens and closes, and that will snug up against the shoulder on the focuser. That's how it tightens up. And of course it's spring-loaded so that it stretches that timing gear so the timing gear's tight. There's also a curved slot at the back there so that it can rotate around an axis. All right, good. So let's watch it work. Here's the power. Here's the control box. Turn the power on, and we can turn it one way. See how it goes? Turning the coarse focus adjustment, just like that. So this is a hands-free adjustment now once this is attached to the telescope. So at this point I'm going to stop and say, any questions yet? Yes, sir.
Are you trying to make that wireless?
Wireless, yeah. Well, that means that the battery's got to go on it. It's heavy, But that's, you could do that.
You need a strong bat. How much wattage do you need?
Well, there's two, you can't see it, but there's two 9-volt batteries under here. Like on the bottom of this thing, there's two 9-volt batteries. You'll see them in a couple.
Do you use to power the motor, or is most of that for the...
Motor, for the current. Yeah, the actual microcontroller, milliamps, 5 milliamps.
2 9-volts to power a motor like that? You really need that much?
You need current. Yeah, you do need current. Okay. Any other questions just for a sec? Anything? Nothing? I'll keep going. No one's going to ask me why I didn't turn the fine adjustment, the fine coarse adjustment? No? Okay. Lights? Well, I thought somebody was going to ask why I didn't attach it to the fine adjustment. Yes? Well, I thought you might ask that, you see. So what I did was I had to add another piece of lucite and another piece of aluminum and another hunk of this bracket. Here's the two 9-volt batteries underneath. You can see that down there, right? But in fact, yes, I did attach it to the fine focus control. And you can see it turning, right? Again, very, very delicate. All right, so you can see it turning. All right, and I'm not going to do it the other way, but it does in fact turn the other way. Okay. Okay. I mean, this is starting to look crazy already. I mean, if you go back and look at this, we got screws and wing nuts, and we got lucite, and we got more lucite, and we got bolts, and we got plates, and we got brackets, and it's like it's getting way too complicated. I mean, it's crazy. So what am I going to do? What am I going to do, right? Okay, well, I'm going to start from the beginning. And what I did was I built a brand new focusing mount. This one was the prototype. I printed each of these little pieces that you see here individually and glued them together with crazy glue according to all my measurements. I then fit it to the focuser, and I could see where it could be modified, adjusted, played with a little bit. So I went back to the computer, I changed the files, I changed things here and there, and when I finally got it the way I wanted to, I printed it as one single, complete, solid piece. So this is the production model, one solid unit. And this is my printer, again, working. It can show you, you can actually see it. It's not the best video in the world, but it shows you how the bed moves, and it shows you how it goes across and lays down the plastic in layers. Builds it up. All right, okay, enough with that. We've seen that already. Okay, so let's watch it work. Okay, you can notice that rounded shoulder. That's where that's going to sit. There's a tension adjust knob that can come out. Let's take that out. Put it down. Let's have it roll off the table. This coupling goes on. Everything's press fit. Yep, there it goes. On the floor. There's my head. There's my head. Okay, so we can screw that tension adjustment knob back in. It holds everything nice and firm. Okay, I did not need really to make this piece, but I did oh, there goes the next one. Just for fun, I put on an additional bracket to hold it on. It's not necessary, but I thought, well, just for solid support. That'll screw in. Let's pick that other one off the floor. Okay, retrieved. Now we get that motor control box. I think we'll just plug that in now. There's those two 9-volt batteries I was telling you about. Turn it on, and can you see it work? If you look right here, you can see the light as it's rotating, right? It's a little hard to see, so what I'll do is I'll show you a close-up. Here's a close-up. You'll be able to see it better. There it goes. There, you can see it a little better now. You can see it. Just like that. And then, of course, it does go the other way. Okay. So, That's basically what I have been up to. And I will now answer questions for you if there are any other questions. All the questions have been asked. Okay, go ahead.
How long was it sort of from concept to end? Like how many hours, days, weeks?
Oh, that Lucite one, the original Lucite screw-on one, probably took about 2 weeks. Just, in the evenings, just measuring and, cutting and gluing and, stuff like that. The 3D printed one probably took about 1 week to do. I had to think about it, had to measure, lay it out in the programs, design it, mess it up, learn how to use the program, all that kind of stuff. Yeah, and usually you have to print it a couple of times. That one probably was 4 or 5 hours to print, and so I started at 11 o'clock and go to bed, and of course overnight the power went off for 10 seconds, and okay, got to do it all over again, computers now on the welcome screen, all that. So probably a couple of weeks, I would think. Yeah, so it's just a good waste of time. Is that it? All right, folks. Oh, one more? Oh, okay. Sure. You can, if you're embarrassed, you can always come up to me after the presentation and ask. It's fine.
Yep. How do you deal with if you want to make a big movement? Because in your second design there, I don't see any way that you could spin it manually or at a higher speed.
That's the downside of the second unit. The first unit, because it's spring-loaded, you can shove the spring, it'll loosen up the drive belt. You can play with the course adjustment. This one, it's kind of locked in. Yeah. No clutch, that's right. There's no clutch.
The belt one, when you reverse, was there any play?
No.
I could see on the suction one there wouldn't be any play.
No.
Nope. No play.
No, it was tight. It was good. It was like it's gears on both sides.
Yeah.
Right? There's the splines on the course adjustment, which grab the teeth on the drive belt.
It was direct.
Oh yeah.
Oh wow.
It was like direct drive. It was good. Yeah.
Any schools or university? Okay.
No. I finally made it here. I was supposed to give this talk in February, but there was a snowstorm and they canceled the night. It was one of the only 2 nights they've ever canceled. Then I was going to give it in April, and the computer did not play nice. And I almost went home tonight, but it worked out. It all worked out good. All right, cool. Thanks, guys.